let's move on to slide 25. The glucocorticoids are the corticosteroids that are made by zona fasciculata. I know, we're still in the adrenal gland. Isn't that crazy? Wow. All right, and glucocorticoids influence our expenditure of energy. Okay. Therefore, they have a lot to do with influencing metabolism. All right. And they also have a lot to do with stress, but I'll come back to that. Okay. The efforts of glucocorticoids are really in place to ensure that we keep blood glucose levels fairly constant, even when we are stressed for food, stressed for sources of glucose, okay? So think jail time or my always favorite zombie apocalypse, okay? And glucocorticoids also help to influence blood pressure, specifically by bringing about vasoconstriction. Okay. Now, the good news is the only glucocorticoid made in significant amounts in the human body is cortisol. Cortisol. So that's the one we're going to focus on. Now, let's go to slide 26. Notice that the background of this slide is green. It's a different color than all the other slides. In the corner is an illustration of a loaf of bread and some pasta. Okay? Whenever you see the green background, the loaf of bread, the pasta, you want to think of glucose metabolism. Green means glucose. Glucose metabolism. And I mentioned in the survival kit that there are some evil vocab terms that you need to tackle in 242. Guess what? It's time! Glycolysis. Glycolysis is something you should already feel somewhat comfortable with from, for instance, your 160 experiences. Glycolysis is the process by which, glucose is converted into pyruvic acid. For each glucose molecule, 2 pyruvic acid molecules. Pardon me. Burpee time. Okay, and glycolysis kind of gets the ball rolling for instance, cellular respiration or aerobic respiration. Okay, glycogenesis is the conversion of glucose into glycogen. And recall that glycogen is the form in which the liver stores excess glucose. So really, glycogenesis is the storage of glucose. Glycogenolysis is the conversion of glycogen back into glucose. Hey, liver, give it back. All right? Gluconeogenesis is the production of glucose from non-carbohydrate sources. And here's kind of a nice take home. If we're converting glucose to pyruvic acid, are we increasing or decreasing blood glucose? Decreasing, because we're spending it. If we're converting glucose into glycogen, are we increasing or decreasing blood glucose? We're decreasing. Because we're taking that glucose out of the blood and locking it away, at least temporarily, in the processes, those help us to decrease blood glucose. Therefore, you might be able to infer, what about glycogenolysis and gluconeogenesis? Do they decrease or increase blood glucose? They both put glucose, just via different pathways, into the blood. Okay, so knowing those vocab terms now, we can talk about cortisol. Cortisol, being a glucocorticoid, helps us to cope with crises that render irregular availability of fuel sources, like the zombie apocalypse, okay? Cortisol specifically promotes gluconeogenesis. Therefore, does cortisol decrease or increase? I just made a new word, increase. Decrease or increase blood glucose? It increases, right? Specifically by promoting the formation of glucose from non-carbohydrate precursors. Okay? If we're not taking in glucose via our diet, then we're going to use other fuel sources to interconvert macromolecules. And one of the chief sites, one of the chief organs responsible for interconversion of macromolecules is the liver. But what doesn't the liver do? It's amazing. In other words, cortisol, not surprisingly, helps to ensure that glucose levels in the blood stay steady even when our supply of glucose is poor. Why do we want to keep blood glucose levels steady? Well, because there are some cells in the body that insist on having glucose as a fuel source. Can you name one of those cells? Yeah, neurons. Neurons will only utilize glucose as a fuel source. So if we want our nervous system to continue to function, we have to make sure glucose is available. Okay? Another action of cortisol is to cause vasoconstriction and therefore help to maintain relatively high blood pressure, just to ensure that those fuel molecules get to their targets as fast as possible. Let's move to slide 27. These weird symbols were arrows. Okay, but obviously ACTH, because it targets the entire adrenal cortex, will promote the secretion of cortisol in addition to all the other corticosteroids. And ACTH is secreted in response to CRH from the hypothalamus. Okay? Cortisol levels, when they rise, they feed back, negative feedback, to the hypothalamus and the anterior lobe of the pituitary gland to say, okay, that's enough CRH. Okay, that's enough ACTH. We've got enough cortisol now. And cortisol secretion is not surprisingly reflective of our eating patterns, our activity patterns, okay? And therefore, because we tend to have fairly predictable eating patterns, fairly predictable activity patterns, we also have fairly predictable cortisol patterns. We tend to see cortisol in its highest shortly after, or actually shortly before we wake up and get out of bed, and then at its lowest right about the time when we go to sleep. And all of that, of course, is a possible exception in your case because you're a college student and probably have a very strange schedule. Okay, trauma can actually interrupt our normal rhythm and therefore interrupt our normal cortisol pattern. All right. Let's move to slide 27. Are we on 27? 28, sorry. Gonadocorticoids. Gonadocorticoids are weak androgens. They're like precursory male sex hormones, okay? And they can be converted, because they're weak, into testosterone. They can even be converted into estrogens, all right? They are secreted, obviously, in response to ACTH with all the other corticosteroids, okay? And the amount of sex hormones that we make via the adrenal gland is fairly minor, fairly insignificant compared to the sex hormones that we make via our gonads, at least from puberty on, okay? These weak androgens definitely have a role to play in the development of secondary sex characteristics, which we'll talk about in just a brief while. A role to play in sex drive in women, because women do make testosterone, just not in as high levels, and also provide sex hormones in postmenopausal women. Let's look at our next slide, 29. Sorry for that pause. I was trying to find it. It's the next slide. Anywho, the adrenal medulla, so like the core, right, or the middle of the adrenal gland. Here's our preganglionic neuron of the sympathetic nervous system. I hate this notation. Since S and S could be somatic or sympathetic. Rude. Actually, let me clean this up. I'm making a mess. Okay, and then at this scale, if we're going to see the entire adrenal gland, we can't actually see the neurons that are in the adrenal medulla. Okay, so nervous tissue. So in other words, the postganglionic neuron would actually belong to the adrenal medulla. Okay, and the products are epinephrine and norepinephrine, which are almost identical, okay? No matter what, whether it's epinephrine or norepinephrine, what do? They trigger blood vessels to constrict. They increase heart rate. They increase blood pressure. They shunt blood to the brain, the heart, and skeletal muscle. I don't know about you, but I'm thinking fight or flight, which is not surprising. They cause blood glucose levels to rise because we're about to spend. Okay. The cells in the adrenal medulla that produce and secrete epinephrine and norepinephrine are called chromaffin cells. Okay. And all of these general effects are brought about by both epinephrine and norepinephrine. Okay? By the way, these are water soluble, even though the slide doesn't indicate. In other words, the adrenal gland makes both lipid soluble and water soluble hormones. Where are the lipid soluble hormones made? In the cortex. Where are the water soluble hormones made? In the medulla. About 80% of the medullary products are epinephrine, and about 20% are norepinephrine. Epinephrine is actually more potent, more powerful, okay, even though, yes, that's what we make most of. And epinephrine is a little more influential on metabolism and also will more specifically bring about bronchodilation, the dilation of bronchioles, okay? And norepinephrine is a little more so concerned with bringing about vasoconstriction in peripheral areas rather than core areas of the body, okay? But again, in general, they bring about the same effects. Slide 30. Slide 30, if I remember correctly. Yeah, this slide has a typo, and I like to leave it there because I like to sort of test students' understanding of what we've recently discussed. Okay, and we'll get to that in just a moment. This is really giving us a contrast between the stress hormones, if you will, okay? In response to stress, typically prolonged stress, zombie apocalypse, the adrenal cortex will secrete what? Yeah, cortisol. Okay? In response to stress, typically short-term stress, so there is currently a zombie chasing you, or you have an exam today, the adrenal medulla will secrete what? Yeah, norepinephrine and epinephrine, okay? So the stress hormones are cortisol, norepinephrine, epinephrine, okay? And some of their impacts are the same. Cortisol increases blood pressure. Medullary hormones increase blood pressure. Okay? Cortisol increases blood glucose levels. Medullary hormones increase blood glucose levels. Okay? But how? How does cortisol increase blood glucose levels? Via gluconeogenesis. Whereas, how do norepinephrine and epinephrine increase blood glucose? Via glucogenolysis? Is there something called glucogenolysis? Oh, I think I found the typo. Right? What should this say? Glycogenolysis. Glycogenolysis. What is glycogenolysis? It's the conversion of glycogen back into glucose. Okay? So same effect, just different routes to actually achieving that effect. Okay? And then some differences, right? Some of the targets are a little different. Okay? But overall, very similar responses. Okay? Good. Now, on slide 31 is the URL for a movie, a video, okay? And just in case the URL doesn't work, what you're looking for is called Stress, Portrait of a Killer, okay? You are responsible for watching this movie. It takes about an hour, if I remember correctly, okay? And it therefore will show up, questions about it will show up on exam 1. Well, whenever an instructor tells me I have to watch a movie or watch a video and that I will be tested on it, I freak out because I don't know, am I supposed to know like the timestamp when so-and-so was dissecting a rat? Am I supposed to know everybody's middle name? Who's in the movie? What particulars do I need to know? And so, this is what I need you to pay attention to. Pay attention to Robert Sapolsky's baboon study. What was he studying? What were his main findings? Pay attention to the Whitehall study, a study of the British Civil Service. What were the major findings? Okay? And pay attention to Elizabeth Blackburn's telomere study. Who was she studying? What were her major findings? Okay? All right, let's move on to slide 32. I totally meant 31. Didn't I? Nope, 32. The pineal gland. The pineal gland. Again, shaped much like a pine cone and kind of textured, and that's between the shape and the texture, it ends up looking like a pine cone. Okay, it's right here. It's part of the epithalamus if you have bells from 241 to ring, okay? And it makes melatonin, which is a little strange in terms of classification, but the best classification for it would be water soluble. Melatonin, you probably already studied a little bit in 241, so you probably already know that it helps to regulate sleep-wake cycles, along with the hypothalamus. The hypothalamus also influences sleep-wake cycles. Melatonin is highest at night. It's highest at night, okay? So it you might think of it as being our natural sleep drug, okay? And it's likely that melatonin, in addition to sex hormones, affects when we undergo puberty, and therefore when we develop secondary sex characteristics, which I will talk about soon, I promise. I didn't forget. I know it seems like I did. Also, probably has an impact on our patterns, our temperature patterns, our activity patterns, our eating patterns, much like, for instance, cortisol, okay? And may also impact whether we're making antioxidants, which are, they're the enzymes that will help to degrade or really claim free radicals. All right, if we move to slide 33, we can see the pancreas in the context of the digestive system. We can see that, yeah, it's pretty dang hidden by the stomach, okay? So if we use our x-ray vision, then we can see a little better what its form is, okay? Notice that it's right up against the spleen. Oops, my pencil does not want to function here. There's the spleen, okay? And really sitting underneath the stomach, and then also is right up against this portion of the small intestine, which is called the duodenum, or some people say duodenum, I don't care. Anywho, we will come back to it automatically when we're in the context of the digestive system. But the pancreas features actually 3 different kinds of cells. Acinar cells. Sorry, my symbols didn't work here. That's no fun. Alpha cells. Beta, Greek beta cells. Acinar cells, alpha cells, beta cells, okay? Acinar cells make pancreatic juice or pancreatic enzymes. In other words, they have a role to play in the digestive system, okay? In fact, in a really, really important role, because the pancreas makes a lot of different kinds of enzymes, arguably a greater variety of enzymes than any other digestive organ, okay? But housed within the pancreas are clusters of alpha and beta cells that are called islets of Langerhans. Islets of Langerhans. And they are endocrine in function, okay? Whereas acinar cells do have ducting associated with them, and therefore they are exocrine in function, and anatomy for that matter. The job of alpha cells is to produce and secrete glucagon. Okay, and the job of beta cells is to produce and secrete insulin. Both glucagon and insulin are water-soluble hormones, and both influence glucose metabolism. They just don't influence glucose metabolism in exactly the same way, and therefore they are not great examples of antagonists. They're not true antagonists, okay? If we look at slide 34, this is a micrograph of the pancreas, which you, by the time you take the practicum, should be able to recognize through a microscope. Okay. And this guy, this sort of island in a sea of acinar cells, these are all acinar cells, okay, is an islet of Langerhans, or a pancreatic islet. Either way is fine. I don't care. Okay, and therefore a cluster of alpha cells and beta cells. Okay, I'm never going to ask you, is this particular cell an alpha cell or a beta cell? I just need you to know that in an islet of Langerhans, we will find both alpha cells and beta cells. And I do also need you to know which cells produce what. Acinar cells, again, produce pancreatic juice or pancreatic enzymes or enzymatic juice. Any of that's fine. Alpha cells produce and secrete glucagon. Beta cells produce and secrete insulin. And I can remember that because alpha is essentially the letter A, and only glucagon has an A in it. Insulin does not. And then I also do something silly. Good old Insulin. You do what you have to do. All right, now notice that on the next slide, slide 35, I've actually placed a micrograph of the kidney, which is also practicum worthy. The only reason why I put, excuse me, this image here is to drive home, dang, the pancreas and the kidney look really similar. Okay, here's an island, right? Both this island, which is actually a glomerulus, ball of capillaries, a network of capillaries shaped like a ball, the ball of yarn in the snake's mouth, okay, and this island, the islet of Langerhans, they both look kind of walnutty, or they both look kind of like a cerebrum, okay? So the difference isn't really whether those sort of islands are there, whether those clusters are there. It's a difference in the ocean that surrounds that island. Notice that acinar cells, they don't form very distinct tubes, whereas in the kidney, the glomerulus, that island, if you will, it's surrounded by tubes. Lots and lots of tubes. All of these tubes are just cross sections through the renal tubule, through the body of the snake. Lots and lots of tubes. Okay? So I imagine that both the glomerulus and the islet of Langerhans are hot vacation spots. I would go to either of those islands. Okay? But when I'm in the pancreas, I do not go inner tubing in the ocean. When I'm at the kidney, I do go inner tubing in the ocean. Okay? So it's all a question of whether there are very conspicuous tubes surrounding those island-like clumps. All right? Now, on the next slide, which is slide 36, I've just given myself some blank space so that I can finally talk to you about secondary sex characteristics. And in order to understand secondary sex characteristics, we've got to also clarify what primary sex characteristics are. Primary sex characteristics are outward expressions of sex that are, but not necessarily gender, that are present at birth. They are expressed at birth, okay? Whereas secondary sex characteristics are outward expressions of sex, but not necessarily gender, biological sex, that is, that do not become expressed until puberty, okay? For males, primary sex characteristics would include the penis. It's present at birth. The scrotum, present and conspicuous at birth. And for that matter, nipples, present and conspicuous, obvious at birth. For females, labia are present at birth. The clitoris is present at birth. So erectile tissue is present at birth. The vaginal opening, which some people mistakenly call vagina. Vagina's internal, not external. And nipples, wait. Why do males and females have nipples? Because males, they start out as females, and it's not until we're in maybe week 7, week 8-ish of development that if we're coded to develop as male, we then veer off of the female tract and head down the male tract. And those few weeks give us enough time to form nipples. Isn't that cool? I think it's cool. All right. Whereas secondary sex characteristics for males, facial hair, axillary hair, what does that mean? Do you remember what axillary or what region axillary is? Yeah, armpit. And pubic hair, they all develop. Puberty sees an increase in muscle mass in males. Puberty also sees the formation of the laryngeal prominence. The larynx becomes larger and beefier, and therefore stretches out the vocal cords and lowers the voice. The laryngeal prominence is also known as the Adam's apple. Okay. Enlargement, not to be confused with the engorgement, but enlargement of the penis and activation of which sweat glands? Do you guys remember sweat glands? Apocrine sweat glands. they become and stay active. But they become active at puberty. Oops. Okay. Female secondary sex characteristics, development of axillary and pubic hair, breast development, activation of apocrine sweat glands, widened hips, now another topic that we can go off on a huge tangent on, coupled with the development of secondary sex characteristics, are some other events. At puberty, we become able to make kids. We can develop offspring, okay? And that means that for males, this isn't a secondary sex characteristic, so I'm going to kind of put it sideways so you don't accidentally put it on the same list. They start making sperm. Okay, they start and continue making sperm, okay? Whereas females, they started the process toward making ova before they were even born. However, they did not finish that process. So when you hear someone claim that we are born with all of the eggs or ova that we are ever going to have, that's actually a very misleading statement. Human females are not born with any ova. 0. We are born with oocytes. An oocyte is an almost egg, for lack of a better description. It's sort of like a precursor that is generated via part of meiosis, okay? Meiosis is started in the womb, in utero. So, fetal female starts meiosis even before she's born, okay? But meiosis gets paused such that the only thing that's been made by the time she's born is oocytes. Lots of them, but they're not ova. They're almost ova. They're oocytes. Okay? Well, when does she hit the play button again? When does she unpause? That's right, in puberty. Okay? And henceforth, every month, her body's going to allow just a small handful of oocytes to continue down that meiotic pathway. And hopefully I'll bring this up again, but much later. Anywho, primary versus secondary sex characteristics. Now, let's look at our next slide, because believe it or not, we're still in glucagon and insulin land. And that slide is 36, okay? Oh my gosh, it's got a green background, it's got bread in the corner, it's got pasta in the corner. That should make you think immediately, oh, glucose metabolism, right? Glycolysis, glycogenesis. Do they decrease blood glucose or increase? They decrease blood glucose. Glycogenolysis, gluconeogenesis. Do they increase or decrease blood glucose? They increase blood glucose, okay? Well, glucagon, it's stimulated by lower than homeostatic norm, low blood glucose levels. It can also be stimulated, the secretion can be stimulated by higher than normal amino acid levels. God, I hate this notation. Or even just the sympathetic nervous system can say, hey, dude, glucagon, please. Okay? And glucagon responds by increasing blood glucose. Increasing blood glucose. Well, there are different ways to increase blood glucose. Which pathways, which mechanisms does glucagon encourage? Actually, both. It encourages both glycogenolysis and gluconeogenesis. Okay? And specifically, it's targeting the liver. Okay? Next slide, 38. Insulin, its stimulus, the stimulus to secrete insulin, is high blood glucose, an increase in blood glucose, okay? And when we make insulin, we actually first make pro-insulin and then cleave it, cut it in half so that each pro-insulin molecule actually yields 2 insulin molecules, okay? Insulin brings about the lowering of blood glucose. And because the ultimate effect of insulin is the opposite of glucagon, many people, including our authors, will describe glucagon and insulin as true antagonists. However, insulin doesn't have the same target as glucagon per se. Insulin really targets almost all of our cells, especially our adipose cells, especially our muscle cells, okay? And what it does is it acts as a sort of permission slip that allows those cells to uptake glucose. Without that permission slip, those cells are not going on the field trip. They can't claim glucose, okay? Insulin also inhibits the breakdown of glycogen into glucose. In other words, what does it inhibit? It inhibits glycogenolysis. And in that sense, yeah, I can see an antagonistic relationship between glucagon and insulin. It also inhibits the conversion of amino acids or lipid building blocks into glucose. What's that called? Oh, that's gluconeogenesis. Oh, okay. So in that sense, I can also see that there's kind of an indirect antagonistic relationship between glucagon and insulin, or at least they're antagonistic where the liver is concerned. Okay. Let's go to slide 39. This image is from the same publisher, but not the same book. This isn't in our book, unfortunately. But this image is really helpful because insulin and glucose uptake by cells, just fascinating. Inside our cells, at least the bulk of our cells, we have a vesicle, among other vesicles, okay, that has embedded in it some proteins that are called GLUT4 transport proteins. GLUT4 transport proteins, okay? So here's our target cell for insulin. All right? And sure enough, there's a transmembrane protein. The receptor site or surface is exposed on the outside of the target cell, as we would expect for a water-soluble hormone, okay? Glucose is available, but what is missing? There's no insulin. So is this cell taking up glucose? No. Whereas when insulin is available, oh, look, here it is. It's bound to our receptor. That binding via, obviously, a G protein-related cascade, okay? It tells our GLUT4 vesicle to start moving toward the plasma membrane. The vesicle fuses with the plasma membrane and therefore installs into the plasma membrane our GLUT4 transport proteins. And now that those are installed, yes, temporarily, glucose has channels to allow it to enter these cells. Isn't that fascinating? Because hormones degrade, yes, insulin will degrade, and yes, we're going to reform these vesicles and bring them back into the cell. In other words, the installation of GLUT4 transport proteins is, again, temporary. So cool. Let's go to slide 39. Insulin is not a necessary permission slip in the liver, in the kidneys, or in the brain. And if it helps, you can think of it as these are sites that need access to glucose either as fuel or to monitor or even to eliminate excess. Okay, so these are different sites that need access to glucose for one reason or another. All right, and insulin, it also plays a role in memory, in learning, in the development of neurons. Okay. Insulin release is obviously stimulated by high blood glucose. That's the chief stimulus. But if we see an increase in amino acids in the blood and or fatty acids in the blood, that will also promote the secretion of insulin. If the peripheral nervous system is secreting acetylcholine, that will promote the release of insulin. The release of glucagon actually promotes the release of insulin. Another argument that maybe these are not the best example of antagonists. Epinephrine promotes the release of insulin. Growth hormone, thyroxine, what the heck is that? Oh yeah, that's T3, okay? And glucocorticoids, who does that make you think of? Cortisol. They all promote the secretion of insulin, whereas growth hormone, inhibiting hormone, and the sympathetic nervous system, they inhibit the release of insulin. Okay? And one way to think of that, especially where the sympathetic nervous system is concerned, you have to defend yourself against, obviously, a zombie. And therefore, you've got to use your nervous system like crazy, right? Well, in order for the nervous system to function, you've got to make sure glucose is available, right? So brain doesn't need insulin to take up that glucose. Let's make sure the other cells, or at least many of the other cells, don't rob the neurons of that glucose in the meantime. Slide 41 is just one of those homeostatic balancing beam illustrations that are included in our chapters when we're talking about homeostatic imbalances. But I think you'll be okay. I don't need that particular one personally. Okay, slide 42. Let's finally talk about diabetes mellitus. And honestly, we could make an entire lecture on just this. So this is really just going to be cursory. There are two types of diabetes mellitus, type 1 and type 2. Type 1 and type 2, okay? And personally, I like to write them like this. Type type 1, Roman numeral 1, okay? And type 2. And the reason why I like to write them this way is because this actually helps me remember the difference between the two. In the case of diabetes mellitus type 1, insulin is not being made in high enough amounts, okay? There's just not enough being secreted. We're under-secreting. Another way to say that, hypo-secreting or hyposecretion. And what I like about writing my types as Roman numerals is that the Roman numeral 1 looks a heck of a lot like the letter I. How many letter I's in the word hyposecretion? Only one. Okay? In the case of diabetes mellitus type 2, insulin is present, but it's not effective. It's faulty. It doesn't do its job. It doesn't bind successfully. Okay? And so rather than being under-secreted or even over-secreted for that matter, its activity is what's hindered. It's hypoactive. How many I's in the word hypoactivity? 2. Oh, Roman numeral 2 looks like 2 letter I's. Literally, that's the trick I use. Okay? In either case of diabetes mellitus, blood glucose will remain high following a meal because that glucose isn't being claimed. It isn't being taken in by our cells, at least most of our cells, right? Some of our cells can access glucose no matter what. And when blood glucose levels remain high, the patient has, in general, or what is generally called a vagus response, or a sympathetic response, when they feel nauseous, okay? And the body thinking that, oh no, my cells aren't getting glucose. We don't have glucose. Oh my gosh. The body makes efforts to make more glucose available, even though glucose levels in the blood are already high. So we undergo or pursue glycogenolysis. We undergo or pursue gluconeogenesis. We even undergo or pursue lipolysis, really in an effort to achieve ultimately gluconeogenesis. Okay? And therefore, that already high blood glucose level increases even more so. All right? And often an early indicator that a patient may be diabetic, or at least where diabetes mellitus is concerned, is that extra glucose in the blood is spilling over into the urine, and that's called glucosuria. Now, this next slide, 43, I only put this, if I remember correctly, I only put this in here to teach you the whole eye trick, but I just took care of that, so I don't need that slide. Let's go to slide 43. There are 3 cardinal signs of diabetes mellitus: polyuria, polydipsia, and polyphagia. Polyuria is high urine output. Where did we see polyuria previously? Yes, diabetes insipidus as well. Polydipsia is excessive thirst. Where did we see excessive thirst previously? Yes, diabetes insipidus. No wonder it's called diabetes, okay? Polyphagia, however, is excessive hunger and excessive consumption because the body thinks we're starving, okay? Not typically a symptom of diabetes insipidus, but a very typical symptom of diabetes mellitus. Excuse me. In severe cases of diabetes mellitus, words, fatty acids and breakdown byproducts like ketone bodies will spill over into, again, the urine, okay, and even threaten acidosis. No thank you. Can therefore be life-threatening. Slide 45. Personally, I don't get too much out of this flow chart, but certainly it helps to drive home our 3 cardinal signs. Okay, let's move to slide 46. The gonads make sex hormones, often referred to as gonadal hormones, just to keep them separated from gonadocorticoids made by the adrenal gland. And gonadal hormones, as well as gonadocorticoids, are lipid soluble. Okay, they're the same. They come from the same sort of precursors that we see in the adrenal cortex, specifically the zona reticularis. Okay, pardon me. In ovaries, the main gonadal hormone being made are the estrogens. There is no one hormone that is best called estrogen. Estrogens, it's a whole group of estrogen-like hormones, okay? And estrogens help in females to bring about the expression of secondary sex characteristics, which we just covered, okay? And also cooperate with progesterone and other sort of female sex hormones, or sex hormone, I should say, to influence cycling, ovarian cycling, and uterine cycling. In the testes, yes, I just skipped this, I'll be right back. The chief gonadal hormone produced is testosterone. Okay. Also, influences the onset of secondary sex characteristics, influences sex drive, really in both males and females, okay, and is influential for spermatogenesis. And we'll come back to that automatically, really at the end of the quarter. Now let's jump back to the placenta. The placenta is kind of a weird endocrine organ, as I actually stated in the last file, because it's temporary, right? It goes away. And it's in place to act as an interface between fetal bloodstream and mama bloodstream, okay? They don't share a bloodstream. They have an interface, and that interface is the placenta. But in addition to acting as an interface, the placenta itself also secretes estrogens, progesterone, and human chorionic gonadotropin. And the chorion is one of the extra embryonic membranes that surrounds an embryo. When we say, my water broke, or my waters broke, or strip the membranes. Okay, the chorion is one of those membranes. Okay, one of the sort of fluid-filled sacs that we associate with a developing, really mammal. Anyway, we'll come back to that as well much later in the quarter. Let's go to slide 47. Kidneys have 2 chief hormones that they produce. Renin, okay, which hopefully we feel semi-comfortable with, because hopefully we've been studying our butts off and we know our 4 aldosterone regulatory mechanisms, including the renin-angiotensin-aldosterone mechanism. The kidneys also produce erythropoietin, and erythropoietin promotes the process of erythropoiesis. Erythropoiesis is a more specific subset of hematopoiesis. Hematopoiesis is the production of blood cells. Erythropoiesis is the production of red blood cells. Okay, and erythropoietin is a hormone that promotes erythropoiesis. Let's move to slide 48. Believe it or not, our skeleton also has some endocrine functioning. Maybe you learned that already in 241. The hormone that our bones secrete is called osteocalcin. Okay? Now, osteocalcin is really interesting because even though it's made in bone, what does it target? It targets the pancreas, specifically beta cells. Well, what do beta cells make? Insulin, right? Insulin. Isn't that interesting that the bones are influencing whether or not we can take up glucose? One way to think of that is yellow marrow stores lipids, right? So we want to influence metabolism, right? And another way to think of that is that if bones are especially active, or rather bone cells are especially active, then they're probably spending a lot of glucose. Okay. And interestingly, osteocalcin levels are typically low in patients with type 2 diabetes. Let's look at slide 48. The skin makes cholecalciferol. Okay? Personally, I teach at least the gist of the vitamin D synthesis pathway during typically the first week of 241. That's right, 241. Okay? And I also teach the ammonia pathway, but we'll come back to that. So let's go over that really quickly. In our epidermis, in particular, we house a cholesterol molecule that is a precursor to vitamin D, but it's a really, really early precursor to vitamin D. When that precursor is exposed to sunlight, it gets converted into the next precursor. Therefore, personally, I like to refer to that precursor before it's exposed to sunlight as A. Is that actually what it's called? No. And when it's exposed to sunlight, it gets converted into B. B is picked up by the bloodstream and taken to the liver. I can hear all of my previous 241 students just finishing my sentences. Adorable. Into, let's call it precursor C. Is it actually called precursor C? No! C is picked up by the bloodstream and taken to the kidneys, where C is finally converted into vitamin D. That's why I use A, B, C, D. All right? Vitamin D is not made in your skin. Stop it. Wrong. The synthesis pathway started in the skin. It's not actually made in your skin. Anywho, each of these precursors has a special name. The one we've been calling precursor A is called cholecalciferol. Pretty cool. Now, the thymus, I just squished into this slide because I had so much room, sits on top of the heart. When we're infants, it's actually quite pronounced. It's quite large because it acts as sort of like a boot camp or a training site for T cells or T lymphocytes. Same thing, okay? And I need to train far more T cells when I'm a brand new person experiencing antigens for the first time than when I'm much older and have already met the bulk of antigens that I will meet, okay? So the thymus actually atrophies with age and is actually quite difficult to find during dissection of an adult. Slide 50? I think I was just on 49 and I said 48 accidentally. Slide 50 doesn't exist. It's blank. So nobody cares. Okay, so jazz hands. Woo! We're done with the endocrine system.